Hello everyone, welcome to today's webinar. My name is Paul Bemis and I'm going to be doing a session on reducing data center energy consumption using variable fan drives. Now, there's a little bit of housekeeping before we get started. I'm going to be using a couple different methods here for talking to you today. I'm going to be using PowerPoint, as you can see here. I'm also going to be using the application itself. I have a couple monitors running, and I'm going to be dragging those around, dragging the displays into place, etc. So one of the things that you'll want to do if you want to ask me a question is probably use the chat box. There's a chat box over on the right, and I have it up on one of my displays, and if you enter questions, then I can go ahead and answer them as we go. I like to make these as interactive as possible. Not always easy to do. I've tried using audio before, and when I open up the audio lines, there's a lot of feedback. So I think that chat is the best way to do it. You can also raise your hand, and I'll be able to see that. So please go ahead and use those features, and we'll go ahead and get started. So first of all, just a little bit about the company. Most of you know us at this point. We've been around since 2008, coming up on 10 years, and we build the CoolSim application. We are a partner of the ANSYS Corporation. We use their technology underneath CoolSim, particularly on the host. We use their mesh solve post technologies, and our job is to focus on delivering very, very easy to use, cost-effective solution for the modeling of data centers. There is other work we do, but it is primarily data centers that we're focused on. The model of delivery that we use is called Saas, Software as a Service, and it is a method that allows you to keep the costs down, which we're very sensitive to your cost of using the software. It allows all of the heavy computation to be done on the host. It is a client-server application. You work with a model builder, which I'm going to be showing you locally. And when you want to simulate, you submit the job for computation through an automated interface that we've created. There are many benefits to this. I won't go into them all, but suffice to say that it has been a very, very effective solution for this target market, and people really like it. All right, so our background is CFD. Personally, my background is mechanical engineering and electrical engineering. I was first a mechanical engineer and worked in the field of electronics packaging, and then became an electrical engineer, worked in high-performance computer design, and ultimately went to work from Hewlett-Packard to ANSYS, and then from ANSYS to Fluent. And then Fluent was acquired by ANSYS, so I've been around this company now for about 20 years, off and on, and have been on my own for the last 10, and working with them as a partner. So that's a little bit about us. Now, I'm going to be talking today about PUE, among other things. I want to define these things as I go. PUE is power utilization effectiveness, and it is total energy facility power, total energy going into the data center divided by IT energy. So what's total? Well, it's certainly the IT equipment over here on the right. You've got all that IT equipment. And then on the left, all the stuff to keep it sort of healthy. You've got to get the energy transformed, but more importantly, you've got to keep it cool. These things run hot, they're getting hotter all the time. And so cooling becomes a dominant characteristic. This came from Uptime Institute. It's quite old, but still valid. 75% of the non-IT load goes to cooling the data center. So if you want to sort of assume these other things are getting more efficient, which they are, by the way, UPSs and PDUs are getting more efficient, then it sort of turns into cooling power plus IT energy over IT energy. That's what it turns into. PUE has gotten some criticism because, you know, you can make this thing look very different depending on where you are with your IT loading, because cooling power doesn't change all that much, but your IT loading, you know, how heavily your data center is filled with IT equipment can vary quite a bit. Now, this has caught the attention of some people on the ASHRAE TC99 committee, and the 90.4 specification looks at just cooling power over IT energy. That's what they call the mechanical load component. They have both a design and a measured component of this. But over time, there's going to be more focus on, is the data center TC 90.4 compliant? And so we're going to be talking about those parameters today. And it is really cooling power divided by IT energy that makes that all happen. Okay. So let's talk about cooling power for a moment. What goes into cooling in a data center? Total cooling power is fan power. These are the fans on the air handlers. Now I'm typically talking here about chilled water data center with air handlers in the room, or air handlers providing the cooling for the equipment in the room, for the white space. And so you need that fan air handler power plus the power required to dump all that heat out. So this is the cooling load up here, is all the stuff in the room, everything that needs to be dumped out or pumped out by the heat rejection system. COP is the COP of the chiller. That's a coefficient of performance. We'll talk more about that in a moment. I've subtitled it CH. It's really the chiller, in this case, coefficient of performance. Now, TC 90.4 has added a few other things to this equation. They've also added in, if you have a cooling tower, the fans to drive the cooling tower. They've also added in pumps. But for purposes of simplicity, we'll just keep it here today. Fan power, which is the dominant one for those AHUs, and I'll show you why in a moment. And then in the numerator, we have cooling load. Now, cooling load in the room is obviously the IT power itself, plus PDU residual. This isn't, people make a mistake here sometimes. This is the heat load from the PDU. In other words, if your PDU is 100 kVA, then only a fraction of that turns into heat, usually around 3%. So your loading here would be 3 kW for heat load on 100 kVA type of device. UPSs, same way. What's the heat load on the UPS? Not what can it handle for load, but what is its inefficiency effectively, the thermal load. And then, of course, fan power. Because remember, you pay for fans twice in a room. You pay once to put the heat in, to put the energy in to twirl them, and then that goes to heat and has to be pumped back out. So that's the cooling load. And so the total cooling power is the energy required to spin the fans on the AHU plus the energy required by the chiller to get all that heat back out of the room. So it's rack power plus PDU plus UPS plus fan power, okay, over the coefficient of performance, the energy required to pump it out. So these cooling units, these chillers, whether it's a DX unit or a chiller, they use shaft power typically to pump heat out. They are heat pumps. A lot of people get confused about this. They think a chiller, they call a chiller one thing, heat pump, they always think about homes and so forth. But in fact, they're both heat pumps. They're pumping heat out from inside to outside. And there is a coefficient of performance that is simply a ratio of its efficiency. In other words, how much work does it take to pump heat? Chillers tend to range from 2, I usually use 2 to 3. I have seen them operate at 4. This is just the mechanical component. As you know, this is not a constant. It changes over the course of the year, and it changes as a function of geography. But we have to make some assumptions in order to design, and so we have to come up with an average COP for the year and then do analysis based on that. And that's what we'll do for the year. In these analysis we're going to do here today. The other law or relationship I wanted to point out is the fan law. And this simply says that the fan horsepower and speed of the fan is a cubic relationship with respect to energy consumption. Specifically, the amount of energy required to drive a fan is equal to the cube of the ratio of the two speeds before and after. In other words, in the reduction case, if you slow the fans down by, say, 20% in fan speed, you're going to see a 50% reduction in fan horsepower. It's a cubic relationship. This is very important because you can save an awful lot of money by slowing the fans down, and that's what you do with variable speed fans. You can do it in pumps as well. Pumps are becoming, everything's becoming variable in this business today because of the energy savings associated with this fan law. So it's important to understand that new horsepower is equal to old horsepower divided by the ratio of the change in CFM or RPM, either one. And RPM is hopefully correlated directly to CFM, assuming your pressure is not too high across the fan. So that's an important one to understand. Now, in order to optimize the data center, we need to first take a look at the airflow in it. And again, we're going to have to use some rules of thumb here. We have to use some assumptions because we don't have exact data on every single server and what it's producing for air. So we're going to assume here 125 CFM per kW as a rule of thumb. That's about a 25-degree delta. We've moved that up a little bit in the most recent revision of CoolSim. We were assuming 20 degrees, and that number therefore was about 156. But servers are getting more efficient. There's a lot of sensitivity in the server world right now, in the design manufacturing world of these machines to make sure that they're more energy efficient. They're using less fan. And so the airflow and the delta T's, the airflow seems to be a little lower, appears to be a little lower, and the delta T's are getting a little higher. So what we try to do in data centers is to reduce the supply airflow to match what is needed by the servers. This does a couple things. It first reduces your fans down, your fan speeds down, and remember that's a cubic relationship, so you get a huge savings from that. Furthermore, it increases the return air temperatures, and the chiller loves that. Remember, a chiller is simply trying to take a specific temperature, use the compression of a medium such as gas to try to bump that temperature up so that it can dump it to the atmosphere and then re-expand it so that it's now colder. It's a heat pump. It's dumping heat to the atmosphere. The amount of pressure that it needs to compress at to get a temperature high enough to dump to the outside air is called lift. And so lift is the measurement of capability of a chiller or a DX unit or any kind of heat pump. So you want to get as high a temperature as you can coming out of the data center to make your entire system more efficient. So what you do is strive to get the airflow where you need it first, and then begin looking at supply temps. How high can I drive my supply temp? Now, 77 degrees has become kind of the actual ASHRAE spec is 80.4 F before there's any issue, but 77 has become kind of the de facto standard for thermostats to begin to drive up the fan speeds on the servers themselves. So we use 77 to be a little bit conservative. My point here is that you don't want the supply air temp to get so high that the servers begin to ramp up. They have variable speed fans in them as well, and they will go up and down. And when they are starting to feel a temperature issue, they'll ramp up. And that defeats your purpose. So trying to get those to as high as you can without exceeding 77 is the way to go. And containment is sometimes used for this. I'm not going to use containment today. I'm going to use a different method. But yeah, 77 is the number that you want to strive for. So a few terms here, just in terms of air management, simple representation here. What you're trying to do is minimize the mixing of hot and cold air streams. You're trying to minimize the recirculation or bypass airflow. So these are two definitions. Recirculation is when the air comes out of the server and just goes around in a circle. This will happen if there's not enough air for the front end of that server for it to breathe. It'll just breathe its own exhaust. This is called rack recirculation. Bypass airflow is when there's too much air and it blows right by. They both have downsides, of course. Bypass airflow means or implies that what happens is you reduce the temperature of the return supply to the chiller or the cooling unit, and that makes it less efficient. Furthermore, you're blowing too much air to begin with, and as you could see from the fan law, that costs a lot of money. Recirculation is the other problem. It's going to breathe its own exhaust, and that's hot, so it's going to exceed rack inlet temperatures over here on the inlet. Now, unless you fully contain, you've got to deal with this issue. Containment is a method, a technique. Containment is you put a separation so these cannot intersect one another, but it comes with its own set of issues, not the least of which cost. So today we're going to take a look at a data center. It's going to be a 7,000 square foot data center. It's got about a megawatt of IT load in it. and it's got natural convection return with a ceiling plenum. I'll show you it in a moment. We're going to perform some baseline analysis on it. The cooling equipment in the room is the CW114s. That's a chilled water system, a chilled water air handler in the room. It's 114 kilowatts of cooling capacity at nominal temperatures. There's 10 of them. We're going to first validate the CFD model if we can. Today we can't because it's a synthetic model. I made it. The point I'm making here is whenever you build a CFD model, you should validate it. You should take it and if you can, if it exists, because in the design phase, they don't exist. So you can do this if possible. Go in and make some measurements of what it is you've modeled to make sure your model is predicting the physical phenomena in the room. If it's not, then the model is not going to predict accurately any perturbations that you try to make to the model. The model should be as complicated as necessary and not more. In other words, you want it to reflect the real world situation as much as you can without getting so carried away that the model becomes too complex and the time to compute it gets too long and it gets too big to handle. You want to perform some baseline energy calculations. And then in this study, we're going to take a look at using VFD to optimize airflow volumes. In a CoolSim 4.6, the new release, we have an ability to do that in the modeler, and it will predict for you the energy delta associated with the change. That's what we're going to show you today. We're going to look at the rack inlets, and we're going to optimize the case until we get to about 77F. And then we're going to stop and see how it looks. So let me, this is the model. I'm going to drag over a copy of the model here so we can have a look at it. I know a lot of you in the room today, the virtual room, are CoolSim users. So I'm going to show you this. This is the CoolSim interface. This is all running local. Again, I only go to the cluster or to the cloud when I need to compute. I'm going to show you a couple things here about how easy it is, and I'm going to do this primarily for CoolSim users, but those of you who are not will see how easy this is as well. And I'm going to set up the VFD here because this is the base model that we've run. This is the input side and this is the output side. Now this has already been run, so these are results. And you will see here that I have a variety of things to choose from, including a full set of 3D results. The model right now is sitting there running at full speed. All 10 are on. It is fully loaded. If we take a look at the data center itself, we see here that it's running at, it's a 6,000 square foot data center. We've got 165,000 CFM coming through those cracks. It's about a megawatt of load in the room, 16 racks. We've got heat load of a megawatt. And the racks themselves only need 139,000, and we're delivering 165. This is always important to look at, the ratio of these two items right here. If any of you have been to DCEP training, you'll recognize this as RTI. RTI is the ratio of these two items, and it is the racks in the numerator, so the ratio is typically less than 1. And up here, you see the 165. So already we know that this thing isn't going to look good from an energy point of view. So here's the energy report. And you see here that the RTI is 84. That should be 100. 100 is perfectly balanced. So we know that it's got too much air. It's not too hot anywhere. RCI, again, for those of you who've been to DCEP training, RCI has to do with how many hot spots are there on the rack inlets. There are none. But it's below spec in terms of cooling, 21%. It's too cold. This suggests it's too cold. Now, if we take a look at our crack performance report here, you'll see we're supplying 60-degree supply air right now. The return temp is 80. That's in that case. Here we're only an 18-degree range. We should be seeing 25 degrees across there, and you see it's 20. So we're supplying too much air. Remember, my delta T on the racks is 25. And the amount of heat being dumped tends to vary a little bit. But let's go take a look at some of the path lines here. So if we take a look at, first of all, this is a plot, and I'll blow this up. This is a plot of rack inlet temp. Remember, I'm not using hard containment here. I just have end caps on these baffles. This is a design that I have seen work very well. It is essentially a convective return. And you see on those rack inlets that they're getting a little into range on the corners, but they're too cold. It's below spec. This is a conformance plot. It's an ASHRAE conformance plot to standard inlet temps. And I always use it to see where I am in terms of rack inlets, the most important thing. And then I typically look at path lines. These are path lines from the tiles right here. And you'll see that I have a lot of air. This is just from the tiles. It should only be going into the rack. And let me just clean this up a little bit in CoolSim 4. You can clean these up a little bit. Let me just take a couple of these and see if I can. There we go. So that's a little bit cleaner shot. And you see here that I've got air going back into the returns in the ceilings and back into the air handlers. That's supply air. You should not see any of these path lines. They should be going just like these, right to the rack and then stopping. That would be a perfect balance. But you see they're coming back in and cooling off those returns. So I'm out of balance right now with respect to that, and it is because these cracks are all running at full speed. So now let's try to add VFDs. And again, I'm just going to show you how easy it is to set this up. Just because, first of all, I think this is a fairly nice way to do it. I switched into top view here so I could see. You see I have a VFD sensor right here. So I bring that VFD sensor into the room. This is just a point, really. We made it a little cube so you could look at it, or a little sphere. And you'll notice it's under the floor at the moment. If I right mouse click in and open the editor for that device, you see it's sitting at -1 foot. Now the reason that's true is because most people use, or many people use, pressure to modulate the VFD, underfloor pressure. I tend to like temperature a little better, so I'm going to use temperature. You can use either one. So I'm going to bring that up to 2 feet. Just get it up in the room a little bit, and then I'm going to put it right in front of this rack right here. So now if we switch into 3D view, and we zoom in over there, you'll see that I've got a sensor sitting right there. That's on that inlet. And most will tell you that you need 3 of them, one in the low, one in the medium, one in the high. I know this gets expensive, but that is what they tell you. So I'm going to use our little clone feature here. This is a very handy little guy. It allows you to replicate with offset. I'm going to provide 2 of those, and I'm going to offset them in the Y direction, which is vertical in our case. Here's my little axes down here. So vertical is Y. I'm going to move it so they're 2 feet apart. That's a 7-foot rack, and I want them spread evenly across it. So I'm going to put those in place. And now I have 3. So now I have 3. Now I can group those together. So here's my group. And I can clone it again. So first let me group it. So now I've got a group and I can clone that group. Now what we know about these racks is they're 24 inches wide. So every 2 feet I want to multiply that across 10. 10 racks, I had to count there. So now we want to go on X every 2 feet, and it's going to clone those right across those racks. So, whoops, I did one too many. Yeah, I needed 9 because I already had 1, of course. So let's just delete that set. So now I can group these. Now to group these, I can just grab them in the top view with a rubber band. I'm just going to rubber band that group right there. It contains all my sensors. I'm going to group them. And then I'm going to offset that as well. I'm going to clone that. This will go in the Z direction. And it's not quite going to be 4 feet. It'll be just short of 4 feet. So distance in Z, let's make that 3.0, let's say 8 feet. We can always adjust it. But there's my other set. Now they're a little close. I really don't want them inside there. So I can just grab them as a set and drag them out a little bit. Put them right there. So now that I've got those set, I can group that set right there. Group those sensors, so there they all are as a group. And these racks are offset by, I believe, 18 feet. So I can now take, whoops, just that set right there, and I can clone them again in the other direction. So now I'm going to clone along X by 18 feet. I think that's the number. And apply it, and I'm going to have another set. No, it wasn't 18 feet, but that's okay. We can drag them over here and put them in position. wherever we want them. And now I have another set. Now I can group those and go down. So here, once I get this offset, maybe this offset was 18 feet, you can put them all in place in a few clicks. Now to map them, let me just show you how that works as well, because it's really quite easy. I'm going to first ungroup them. If I want to map these, I just first ungroup them, and then I right mouse it and say show connections. And we've come up with this very nice little method here for mapping the sensors to the cracks. So you see all my cracks, and a crack and an AHU is the same. It's just a name. They're air handlers in this case. And here are all my sensors that I just laid in there. And what I can do for crack 0 is I can take them all, and we've allowed you to simply scroll to the bottom and use Control-C and Control-Shift and all the rest. So I can Shift, select, and I can say I want crack 0 to use all of them. And it will just move them all right over there. And I'm going to use temperature as a threshold. And then I can right mouse click and say copy the sensor connection. I can take the very first next crack, number 1, which doesn't have anything. I can use my shift key, grab all these guys, right mouse click, paste, connections. Boom. I've done them all. I've just attached the sensors to all of the cracks. That's very nice. And it does it all at once. So now if I look at any one of those, you see they're all hooked up, and they're hooked up on temperature. Now the next thing I want to do here is I want to set a threshold for that temperature. So I want to edit the VFD data itself. I right mouse click it. It says it's not set up for VFD yet. Do you want to do it? Yep. And you get this other little editor. And I'm going to set a threshold here of 75 degrees, not 77, 75. Max flow rate is picked up from the device itself. I'm going to threshold off of peak temperature. I can do RMS, max, min. I want max. If you do average, you're going to have hot spots. I want to take the max point, and I want to apply that. So now I've set it up for one crack, but again, I can copy VFD data from that one. Again, using the same methodology as before, I can select crack 1 to crack 9, and I can paste the VFD data. I have just set up the VFDs for that entire data center. Now, I didn't put all the sensors in place for purposes of time, but you can clone this group and offset it. The great thing about data centers is they have symmetry. So you can use symmetry to your advantage with this offset feature and this cloning feature of CoolSim, and it's very handy. So I just wanted to show that to you, show you, those of you who are CoolSim users, how that works. And that's what that asterisk was for, to remind me to do that. Now on the energy side, I want to take into account this fan energy in the CoolSim model. So I pulled up the fan power section of the CW114 specification to show you how to do that. So here is the CW114. You get this from the Liebert site. They'll always list their fan motors. You need to choose the right one. There are two. This is the older style here with belts. This is the EC fans up here. And so it's important to know which one you're using. Notice they're not that far apart. 3.4 horsepower, or kW, I'm sorry, 4.2 horsepower, 3.4 kW per unit. We have 3 units in each one of these devices. You can see I underlined 3. So we've got 10.2 kW times 10 units. So we've got 100 kW of fan power going into the room that both is really used twice. Once to spin the fans, and then you got to pump the heat back out that it creates. So in the CoolSim interface under Edit, Energy, there is an input dialog. So here's my input dialog, and I am assuming for purposes of this modeling exercise a COP of 3 for the chiller. That's chiller COP right there. 3 is not a bad number. 4 is quite good. 2 is not good. So I have it defaulted at the moment to 3. I put in my fan power 102. I put in measured other power, such as UPSs or PDUs, at 5. I put in the cost of electricity at 10 cents, just to give us a feel for cost. Those things may vary, but that's certainly how you do it. I wanted to show you some efficiencies here. I grabbed some efficiencies. So where did I get my 3? This comes right off Liebert's website. This is their FG chiller efficiencies, and you notice they're listing up here at the top the capacity and the amount of energy required to drive it. Now, this is when it's in, non-economizer mode. And how much it's in economizer mode or not, it depends on where you are in the world. So that's a little bit more complicated. But again, for purposes of optimizing the white space, optimizing the data center, you can assume an average. So you see the COP here, I did the math. It's ranges from 2.4 to 3.1. So my assumption of 3 isn't too bad. You see it varies as a function of ambient temperature, so it depends where you are in the world. So we're going to assume 3 here. And on our base calculation that I was showing you, the RTI was 84. We've got too much air, no VFD in this case. RCI is 22. That's awful. Cost right now to run all those chillers with a full load in the room is 1.4 million, according to 10 cents an hour. Too much air and the supply temperature is too low. Both conditions exist. So now let's take a look at the next set of output here. The first step will be to get that volume down. We're going to assume, as I mentioned earlier, 125 per CFM for racks. We're going to put the temperature sensors on the rack as I showed you, and we're going to begin to run some models of that. So let me show you that model. I'm going to drag another one over. I have all these open. So here is that model. I'm going to put it into full screen mode. You see I've got my sensors in front of everything here, as mentioned before. And all my sensors are showing. And that's on the input side. The output side sits here in this report. So here's the report, and I've got the energy section open right here. But let's take a look at the energy and see what happened. The PUE came down to 1.5. The RTI went to 90.28. Nice. So what this means is that now we're supplying fairly close to what the rack needs. The RCI is 100. That's good. No hot spots. RCI low is 21. It's still too cold. I've got my cold air supply is too low, my supply air temperature. So let's go take a look at our racks again at this point and see what we've got. You see we've got some, again, and this is a design that only has end caps on it. The reason I did this is because you can be quite effective with this design. I am not always an advocate of full containment. We could have put a full contained box around that, but there are issues with full containment, such as pressure, that you get into with these that this system eliminates. There is no pressure issue here because it's open. And furthermore, it's inexpensive. Let's take a look at our air delivered from the tiles again and see what's going on there. So here is air delivered. We're seeing a little bit of bypass airflow. Again, let me clean that image up a little bit so you can see it a little better. These results, by the way, are local now. The results in CoolSim all come back down to the client for review. I'm interacting with them in 3D, of course, but they are all local and they sit right inside the package file. So you see, I do have a little bit of overheating going on there, and I could adjust the VFD a little bit. Remember that the VFD is sensing temperature. We can go take a look at those temperatures in the report again. Would like to. Here's the VFD report, and this will show us what those sensors all are. Every object in the CoolSim system will have a full report on it. And so in the VFD report, we can see the temperatures and what they're modulating at. So you see 75 was the set point. It's modulating to 75. Some of those are colder. It's looking for a max set point, and it'll adjust the supply accordingly. So here is a piece of data right here. So you see we're running at 15.4 on a max speed at 17 to achieve the max temperature of 77. I've got it set for 77 right there in that particular run. So if we go back to the crack report, you'll see that here as well, 15.4, 60 degree supply air temp. Okay. So it's working. working pretty well. We're modulating a little bit. We've brought it down from 17. We're going to see a savings on that. The PUE improved, and that's what we're after, is trying to move it down. You see we went to 1.5 from 1.56. The RTI went to 90 from 84. That was the run without the VFD. The RCI low is still too low, where 60 degrees is too cold. We might be able to increase that a little bit. And we see already from just what we've done, we're saving approximately $50,000 a year. Now, I don't know what it costs to put VFDs in place, but payback on this thing is clearly within a couple of years just putting VFDs in place alone. And this is at full load. I'm going to show you what happens at half load as well, because the new TC 90.4 specification requires that you model it at full load and half load. Half load is more difficult. So that's the initial run. That's what it looks like. We want to increase the supply air temp because we get chiller efficiency improvement if we raise it. The rule of thumb is about 2% per degree F. It's really it's 3.5% for every 1.8 degrees F is what the sort of rule of thumb is. Again, it's not a flat curve, and it has to be within a certain range. But we have to use some judgment here, some engineering judgment, to figure out which way to go just in terms of design. So we're going to assume here about 2% per degree F, and this is again backed fairly good by documentation and ASHRAE. So we're going to try to drive it up. Now, to drive it up, we have a very nice feature within CoolSim that allows you to do this. And I'm going to show you that right here. This is the opportunity in CoolSim to do multiple simulations concurrently is very handy. So in this particular run, what I've done is I've used something called crack parameter variation. And what crack parameter variation allows you to do is vary 4 parameters and up to 4 runs of those parameters. So from one CoolSim model, I can submit 4 variations to be looked at once. And in those variations, I can take a look at supply air temperature, I can take a look at flow volume, and I could take a look at on-off state. So 3 parameters. And in this case, what I'm going to be looking at, and I can run, of course, up to 3 of them at once. And what I'm going to be looking at here is supply air temp. So I have made a set of 4 variations. You can run up to 4. And what I've started to do with all other things constant is I've started walking up the temperature curve on supply air temp. So I've gone from 64, I did it in 2 degree increments. I've got 4 runs here in this one simulation that I've submitted. I've got 4 variations with 2 degree increments on supply air temp happening per variation, per run. So that's the input panel there. Let's go take a look at the output and see. Now, the beautiful thing here is that it all comes back to you in one consolidated report using HTML to summarize it and all of the graphics you'll need to analyze it all together, all at once. So here is, you see in my lower left-hand corner, I have design tab as the input, report is the output. This has been run, it is downloaded, these are the output results. This is a summary page. And you see what's going on here is I'm walking up the temperature. So here's run 0. Let's first go to run 3. I moved it all the way to 70 degrees. Let's see what happens at supply air temp of 70 degrees. First of all, let me take a look at rack inlet temps. Again, what happened to my rack inlet temps? And you see I'm getting some bleeding. I'm getting some, we call these Visine charts for those of you who grew up in the United States and are old enough to remember the Visine ads. They used to always talk about get the red out with Visine. And here we have red. Red is hot. It means that it's outside of the ASHRAE recommended temperature inlet specification. So supply air temp in this case is a little too high. And that's, of course, because we don't have anything contained here. This is a naturally convective environment. And as a result, it looks like we're a little too high on this one. Let's take a look at run 2. I usually go from the top down. Let's take a look at run 2 and see what happens at 68. Now that's not too bad. 68 degrees looks pretty good to me for a couple of reasons. There is a little bit of red, but you don't generally put servers up there, right? This model does assume, by the way, uniform load of equipment across the rack. Now I have distributed the load throughout the room. The load is not uniform. We have a plot for that as well if you want to take a look at how the room is populated with load. I didn't assume uniform load in the room. So I did vary the load throughout the room, and you may or may not want to do this. Again, when you're doing the design phase, it's difficult to know exactly what the real world conditions are going to be. You have to make some assumptions. So what you have to do is use good engineering judgment to try to steer things in a direction that is going to be good for the customer and good for the prognosis of the data center over time. So in this case, what I did, instead of loading those uniformly, is I loaded them in a particular way that varied the load across those racks. And here's a plot of how I loaded them. This is a load plot here. It's called Power View that we have, and you see here that in some areas I'm more heavy than others, and I tried to uniformly distribute the load around the room. So it is assuming that the racks are operating fairly perfectly with respect to leakage. So there's no leakage assumed in this model through those racks at the moment. You can always add it, but I did not assume it here because I'm trying to make another point. I've got the racks sitting on the floor with no leakage underneath them, and they're performing pretty well. I've got end caps on the ends to keep the cold and hot away from one another. But that hot air, if you take a look at any one of these runs, let's go back to run 2 again, and we wanted to look at path lines coming from the racks, you'll see that they're going right up into that ceiling pretty well. So this is hot air coming out of the racks. Again, let me just hide that ceiling so we can see things a little bit better. So we turn off the room and the floor. It gives us a pretty good view. So you see that hot air coming up into the ceiling through the ceiling plenum. I can also hide these blocks here so I can see through those. So there's a pretty good shot of the hot air coming up. It's not perfect. You see it does go other places than into the ceiling, but for the most part, it's behaving pretty well. It's going up into the ceiling. You're getting some wrap around on the front, not too much. We're getting some wrap around over here, around this end. But generally speaking, it's behaving the way you would expect it to. So run 2 looks pretty good. Let's take a look at the energy on run 2. 155, PUE is the same. RCI 99.33, that's very good. Look at RCI low, 100. If those two are near 100, that's really what you want. RTI is a little low. You'd like that higher too, but if you drive this up, it means less supply air, and that's probably going to drive this one down. So these two kind of work against one another. That's what the optimization routine looks like. But the fact that I was able to move up 8 degrees means that I can go back and adjust my chiller COP in the next run, because the chiller COP is going to improve at about 3.5% per 2 degrees, about a 1-to-1 ratio. So that's what you do. You go back now to your COP and you can adjust it up. It ends up being 3.47. If you take 8, do the calculation, you take 8 and divide it by 1.8 and multiply it by 3.5%, your COP will go up to 3.47. That improves your PUE, drops it to 1.5. RTI is not too bad. RCI looks good. So that looks pretty good. Now, the RTI has gone down a little bit because the fans did come up a little bit. There is a trade-off between supply air temp and fan speed, but they remain fairly consistent. And here's a plot here. This is a sort of a summary of what we just did. We had a base model. These are the numbers running at about $1.4 million, $1.46 million a year of operating cost. We added the VFD. It dropped by 60 grand due to fans primarily alone. We increased supply air temp 8 degrees, and it stayed right about constant. Now that is because the fans came up just a little bit, when we increase the supply air temp. So there is a balancing act there between supply air temp and fan speed, but you're pretty optimal right around there. Either one of those two is working fine. Savings per year about 60K. Now 60K off these numbers, assuming that we are at 10 cents an hour. But you can also use percentages. You can always say, hey, save, in this case, 4%. Not a huge number, but we weren't too bad to begin with, as it turns out. I also showed you my COP calculation here in case you wanted to see it. I was able to go from 3 to 3.4 by taking 8, which was the delta, multiplying it by 1.8 F, which is for every 1.8 degrees Fahrenheit of temperature increase, you get 3.5% right there of efficiency improvement. So there's my 3.47. Okay. So that's an optimized case for that one. Now, what happens at 50% load? Now, the reason I bring this up is in the TC 90.4 specification, they also want you to optimize the design for half load, because this is where you get into a lot of trouble. As you just saw, designing for full case loads is actually not too bad. You can get there fairly easily. But what happens is in the case where you want to run less than full load, remember these people don't fill it up overnight, they fill it up over a period of time. How do you handle that in the meantime? And here, there's a question we have to ask is how do we set this thing up? Do we run it with all AHUs on and run them all, or do we run it with just 6 on? And I've seen people do this differently. You go into some data centers that are half loaded, they only have half the AHUs on. Okay. Is it better to have them all on? And we'll show you that analysis here. So at 50% load with 6 devices running, 6 air handlers running, because that's logical that you'd have only 6. If you do the math, that's all you need. In fact, it's a little more than what you need. You run them at 100%, again, it doesn't look that good. Your RTI is 67. You're too cold. Again, I'm assuming a 20-degree temperature here. So you begin to say, okay, well, what if I put VFDs on those 6 units? So the first thing to do is get the VFDs in place. Again, we assume 125 CFM per rack. We put the temperature sensors on every rack and we set it to a temperature. I think I did 75 F here. I'd have to look. Now that helps things right away. So putting 6 AHUs in place with VFDs on them helps a whole lot. And I've got that one here too that I can show you. So here's the half loaded case. I'm going to drag it over. And this is what it looks like. I filled the, again, if you look at it from the top, I filled the top half. I just deleted the other half. You see in CoolSim, there's an arrow indicating that a unit is on. So you see the arrows here are only 3 on each side. So I've got 6 units on. And let's take a look at the output. So here's the output for this particular system. You see the, first of all, data energy report 143 PUE on an assumption of efficiency of 3 for the chiller again. RCI high 100%, RCI low 22, not very good. 669 is sort of the base cost. That's running these things as we did before. If we take a look at the crack performance report, they are modulating a little bit. These go to 17,000 max. You can see they're down around 12. So you know it's working fine. But the question becomes, can we get it to work better? What happens if we go ahead and use the all 10 units? So here, utilizing the VFDs, we improve things, and it's a bigger number. Look, it's 13% now. So it's a bigger deal in the case where you've got overcapacity for the worst case situation in your data center, and then you run it at less than that. VFDs become even more important than they would otherwise. Now, let's see what happens if we do it with 10 AHUs or 10 air handlers. And what we find here is that it actually gets even a little better. We go to 653 instead of 669. That the RCI low comes up a little bit. So actually, it goes down. It gets worse. The RTI is a little higher than we'd like, but we might be able to drive supply temp up here. So that's a pretty good set of numbers, 653. Now let's see what happens if we increase supply air temp by 8 degrees. And what we find in that final case, which I think I also have here, the final case is that one with all of the units running. This is the summary case. This is the full case here, so not this one. I've got a lot of these open. But in the final case, we've gone up 8 degrees. We got to our 347 of COP increase. The RTI went to 83, not too bad. I'd like to see that higher, but look at these two numbers, absolutely 100. And the final number dropped to 611. So that's a pretty optimized case. We went from 155 to 135, and the cost to operate dropped by 14%, or 100 grand a year, if 129, assuming that you assume 10 cents per hour. So that's a summary right there of those cases. We have the base case, 6 of them on at 60 degrees supply air temp, 760. Then we went to 6 VFDs at 60%. Then we took a look at 10. And you see here what's going on is the RTI is changing a little bit. So what happens here is that we end up blowing a little more air in the case of 10. But again, I've got those sensors, 3 of them per rack. The RCI low goes to 100%, even at 60. And then when we go up to 68, it gets even better, 611. So we saved about 20% in the half-loaded case. So that's how you do it. So what I'd like to do is open it up for questions, see if there's any questions. Again, as I mentioned at the beginning, the best way to ask questions, I believe, is the little chat button. There is a little chat button there. I see there are some questions. So I'm going to go ahead and review them. Let me just do the summary here. Yeah, it's fairly easy to do this now, and it is a bit of an iterative process to make sure that you're within that spec. This is going to become more important over time, this 90.4 spec. And these metrics are in CoolSim. You can use them now for optimizing your energy. And it's a great decision tool, a decision support tool. So let me take the questions in order here. I've got one from Jean Fontaine. Has ASHRAE validated the computational fluid dynamics equations embedded in the CoolSim for use for licensed professional engineers in a design documentation for typical project? Answer, yes, absolutely. I was at the TC99 meeting last week in Chicago, and they're using, I'll tell you, just in general, ASHRAE is using CFD everywhere. And CFD is now an accepted representation for physical phenomena. By the way, it has been, Gene, for a long time in aircraft engines and automobiles. I mean, the alternative, I would say to you, is what choice do you have? My point simply is that you cannot use hand calcs, and you cannot guess. And CFD has now become the tool of choice by people designing a lot of different things, because it is now able quite easily to represent physical phenomena accurately. I saw a number of presentations last week where CFD was predicting physical phenomena spot on, not only for data centers, but also for things like instrumentation validation, measuring flow in compared to experimentation, predicting it, modeling it. So yes, ASHRAE does validate this methodology. So what is the shortcut for opening the visibility window? The visibility window, Mike Hackenberg, I don't know what you mean by visibility window. Shortcut, oh, I think I know what you mean. It is this one where you want to see things more clearly. I'm going to guess that it is this one right here. CoolSim has some very nice graphics capability. Again, it comes primarily from the ANSYS Corporation, but let's take a look at some path lines here. That's not a very interesting one, but the one from Tiles is. And I think what you're asking me is how to clean this thing up like I was. It is the E key. E is in edit. E is the editor, and it allows you to turn things on and off dynamically, like blocks and rooms and floors. That's usually what I do. and it gives you a nice clean way to view. And also there's keystroke shortcuts like X and N, which give you perspective. You turn off perspective, and you get a nice clean shot there of what it looks like down the end rails. It's all interactive. This is all local. I'm not looking at anything remotely. You can export these files and open them with Internet Explorer and view them dynamically for a customer or for your own viewing pleasure. What is the maximum rack server outlet temperature that becomes an IT operational problem for rack servers in critical data centers? Gene again. Well, what happens here is the delta T tends to be 25 to up to 30 degrees. So if you've got 70-degree inlet temp, which you'd like to have, then your outlet temp is going to be 110 on some of these servers, and that's getting close to beginning to affect other stuff in the return path. So 30-degree delta T is not uncommon. It is what people are running today, particularly in these high-density servers. And yes, you do need to be sensitive to high temperature on the return path, going by things that might be sensitive to that temperature. Of course, the chiller loves it. The chiller wants it as hot as it can get it because it has to do less work, and the efficiency of your data center will improve dramatically, as well as the window of economizer operation if you're using one. Yes, but generally speaking, 110 is about when they start getting nervous and that's Fahrenheit. In calculating the operating cost, you take into consideration the demand charge that electricity utility charges. No, I don't. Those equations are a little more, detailed. You'd have to put in a function instead of just a constant. But it's algebra. It's not complicated. So that may be something we get in there. I'd actually like to put in chiller curves first, but CoolSim will continue to get more refined with respect to its energy calculations over time. What are common thermostat locations seen in the field that are not optimal? I see a lot of junk in the field, a lot of mistakes. It's quite common to see thermostats stuck in the returns of the crack units themselves. That's a terrible place for thermostat, even if you're now, let me be specific. There's a couple different thermostats that are used typically to control these things. One of them is they're using it to control the VFD, and that's either a pressure sensor or a temperature sensor. You can do either one in CoolSim and either one in the field. If it's a temperature sensor, you should do what I did in this model, and that is put them in a variety of locations. In a design like this one, and yeah, I've only got them up here on this one, a design like this one, you want to be careful at the top of those racks, because that's where you're going to get recirculation, you're going to get overage, these corners in particular. So you want 3, low, medium, and high, across each rack. Now, a lot of people stumble on that because it's expensive. Those sensors are expensive. So they only want to put a couple in. Well, where do you put them? And that's for VFD. Now, the other thermostat they often put in place is the one for chilled water. It modulates the chilled water valve. It is the supply air temp thermostat. Those by default come in the return. Believe it or not, they're stuck in the return of the cooling unit itself, and you've got to move them. Now in CoolSim we have an option where you can move them to the supply. That's generally what people do, is move them to the supply, so that the thermostat that controls the cold air is actually on the supply. And the reason you want to do that is because you want to drive off supply air. You could put the thermostat somewhere else, but you'd need multiple thermostats to get a good feel for what you need, and you'd also need to know which which cooling unit is modulating your particular rack. So I recommend putting the thermostats on the supply, not the returns. And I recommend, I like to drive VFDs off temperature and not pressure, but many of them are set up with pressure. The problem is the pressure is not uniform under a floor. It tends to vary as a function of location. It varies as a function of data center design. For example, if I had all these AHUs on one side, which I have seen, and none on the other side, then you'd have big pressure variations from left to right, and on the right you'd have tremendous pressure under the floor, and on the left you would not. It would build towards the wall. Remember that pressure is, total pressure is a sum of static pressure plus dynamic pressure. If you've got high speed moving air, and I might be able to show you this right in our plot here. I usually plot pressure. Here's pressure under the floor, and you see some variation there. This one's pretty good actually. Let me just use shortcuts to show you. You see here we have high pressure. It's banging against the wall right there, so the pressure goes up. Pressure is fairly high here, or low here. It gets high towards the middle. This is the highest because they're both blowing to the middle, so you have no momentum here. You have no real velocity. That's why it's highest. I was highest in the middle of a room that's got perimeter cracks. So you probably would not want to put your pressure sensor here. You'd probably want to put a few of them under the floor, and it becomes difficult to know exactly where to put them. So I drive off temperature. What are some common thermostat locations? Okay, how do you measure the airflow of each rack? It's difficult to measure the airflow of each rack. None of us really know. This comes up a lot in TC99 when we meet and talk about this. You have to make some assumptions. Specifically, the rack itself, or the server which is in the rack, and you can in CoolSim, create individual servers if you want. So I can go in here and say I want individual rack specifications. And then inside the rack specifications, I can, this is the front face of the rack, and you can say, well, it's really not 8 kW uniform, it's 8 kW across these 7 U's right here. But you must make some assumptions about a heat load and flow rate. Now what we've done is we're assuming a 25-degree delta. And that's fairly conservative. I mean, a lot of people push towards a 30. The amount of flow, and here I'm assuming that it's uniform. In other words, if I move this to 9, it's going to go up linearly. And it doesn't go up linearly. But it's the best we have. This is really all we have without creating a function for each server. And the function for each server would have to be copied from the manufacturer, who's reluctant to give us their algorithm for adjusting flow rate as a function of temperature because it's proprietary. So to be honest with you, Geraldo, we don't know exactly what it is. This is the best information we have. Again, remember that this stuff is a design guide. It's there to help you make good engineering decisions. It's not a substitute, of course. By the way, you can put gaps in here too, as small as 1 U, and model it with holes if you want to. So see, I just moved that. I put the 8 kW right there, and it's got a hole going now right through it because I forgot to put a blanking panel in place. So if you want to add detail to these racks to make them more realistic with respect to the situation you're trying to represent, you can, and it will cost you more in time, of course, because it's more detail. All right, when increasing the supply air temp, if the server speeds up, the additional kW increases inside CoolSim? Yes, exactly. Question from Mark. So what happens is we're using the fan laws inside of CoolSim to do the prediction of cost. So if the supply air temperature goes up, then probably the fans will blow harder. We saw that in our last case. Here they are right here. So here you see we got more efficiency out of the chiller because we increased the supply air temp, but the RTI dropped, which means we're blowing more air. Remember, the rack requirement's in the numerator. So if this thing goes down, it means we've got more air coming into the room. So we went to 82 from 90, and it was a wash in terms of savings. So now this makes an assumption that we didn't get more efficiency out of the chiller, which may happen, particularly if it's an economizer. If it's an economizer chiller and you raise the supply air temp by 8 degrees, it widens the window of time that the economizer gets to operate. And that may change your annual COP quite dramatically. But you can see here a case where, all things being considered and no economizer in play, that you've reached an optimal point. That's as good as you're going to get, whether you tweak the VFDs a little more or if you tweak supply air temp a little more. Now, if we went to containment, we could probably get a few more degrees out of it, and the fans may slow down. But in this case, we're operating, at a PUE at about 1.5. And I've seen these kind of data centers operate this way with fairly good PUEs. So that's why I wanted to point it out to you. Can you explain how to do the same procedure for raised floor design? This was a raised floor design. So they're all the same. I think you might have meant non-raised floor. The methodology is exactly the same. You lay it out the same way. You first try to get your air balance in position. Once you've got your air balance in position using the new VFD controls, then go ahead for your supply air temp and try to move it up a little bit. What is the standard CFM per kW? CFM per kW, in this case, we're using 125. Again, it does depend upon what you're using for a delta T. So let me just see if I've still got that interface open, and I'll show you that one more time. Not that one. How about this one? This is the one I had open. And you can make your own assumption. CoolSim 4.6, in the most recent release, we moved it up just a little bit from 20 to 25 under pressure from the IT manufacturers. But here's a server I just put in there, and you see that the default is 25F. So what's that in C? That's 13 point, it's about 14 degrees, 13.9. You're getting about 125. If we took this to 1, you would see a relationship 123, 124. Okay, so that's the assumption associated with cooling. It's a fairly conservative one. So I think that's still something that works. How significant is static pressure to supply VFD performance? As I mentioned, static pressure I don't think is a good proxy for what's going on in the data center. It's my own personal experience, but as I mentioned, where do you put the pressure sensor? And how tight do you control it? You know, it's a little bit like measuring carbon dioxide in a room to understand how well the humans are doing. Humans don't breathe carbon dioxide, so it's a proxy. Here, pressure is a proxy for inlet temperature. So what I'd rather do is just measure inlet temperature and drive it that way. Now, having said that, it's a cost issue because it's cheaper to put one pressure sensor under the floor than it is to put 3 temperature sensors, one, you know, per rack. That cost adds up quick. But from a control point of view, it's a better control because you're actually measuring what it is you're trying to control, and that's rack inlet temperature. So, and how much is the cost of CoolSim for personal use? CoolSim ranges in price depending on what you're trying to do with it. There are monthly fees. I'm sorry, you can buy a monthly subscription or a multi-month subscription. It ranges from monthly subscription is $4,000 for a single month, $5,000 for 2. Occasional use model is $9,000 per year. So that's a little bit of cost associated with CoolSim. It is the lowest cost tool of its kind in the CFD space by a wide margin, by a factor of nearly 3. So it is the most cost-effective solution, and it is because we built it for occasional users, people who need it occasionally, and we aggregate that occasional use on a cluster for computation. So it lowers your cost of ownership dramatically as well because you don't need to buy any local processing. With other packages, you have to do all the processing locally. So let me just go back to the end here and do the summary slide. I'll ask if there's any more questions. I think I got everything here that I wanted to cover. This TC 90.4 is going to become more popular. Watch your 50% load cases. You're going to want to model those. And if you want to get a hold of me for any reason, try out the software, you want to talk more about it, you have questions that didn't get answered, please let me know. And I think I answered all the questions. If you have any more, just send me a note afterwards and we can pick it up from there. One last question, have you explored using the 1/3 the VFD sensors to see what a sweet spot would be? No, I did not. But you know, after a while you get, from looking at these designs, you get fairly comfortable where the worst spots are going to be. In this kind of design, after you've made the first run, you can see where the hot spots begin to appear. So in this case, the hot spots began to appear. Let's just take a look at one of the reports here. They're always going to be on the edges. You can see them right here. And that's a very normal plot of temperature associated. Now this one, I was cutting down the RTI a little too hard. But you see where it turns up. It turns up on the edges. So putting your sensors up high on a design that's raised floor where the cold air is coming from the floor, probably get away with fewer. Probably don't need them down low. So you might be able to get away with just 1 per rack along the top if I were to try to save money. That's what I would do. All right, I want to thank you all for attending today. I am recording this presentation and we'll make it available on our website if you'd like to see it again. and we are here to help you with your designs anytime you want. Just feel free to reach out to us. Thanks again for being here today, and have a good day.